All right, today we are talking about how to calculate the infinite geometric sums or series and the finite geometric sums or series. So when a sum is an infinite geometric series, this is what we talked about yesterday with the Jake and eating the pie example. The common ratio has to be less than 1, or actually the absolute value of the common ratio has to be less than 1. The part here that you see is simply sort of explaining a geometric series that is infinite. And what you see happening is we have the first term a sub 1, and we are adding on the second term, which is a sub 1 times the common ratio. Then we're adding on the third term, which is a sub 1 times the common ratio squared. Then add on the next term, which is a sub 1 times the common ratio cubed, and so on and so on and so on. That's what the dot, dot, dot means. Until we get to a term somewhere down the line that is a sub 1 times the common ratio n minus 1 times. And then we have plus dot, dot, dot. And that plus dot, dot, dot on the end means that it's going to continue on. And this makes sense to us, of course, because we're talking about an infinite geometric series. And of course, that means it goes on forever. Now, when we identify a geometric series as being infinite, and we mostly do that by recognizing that the common ratio is less than 1, then we simply apply this formula right here. The sum would equal a sub 1 divided by 1 minus r. And we know a sub 1 is the first term, and we know r is the common ratio. All right, here we have two examples. The directions say find the sum of the infinite geometric series. So right off the bat, the directions themselves are telling us that we have an infinite geometric series. But if the directions didn't tell us that, if we had to decide for ourselves, we could, just by looking at the problem itself. When you look at our first example right here, notice the sigma notation. It starts at n equals 1, and on top is the symbol for infinity. Well, that sigma notation means find the sum of the first infinity term. We know infinity goes on forever, so that is a dead giveaway that, again, we have an infinite geometric series. Same thing in our second example. When you look at the sigma, it starts at 1, n equals 1, and it goes to infinity. So that's how you identify that it's an infinite geometric series. And then you simply apply this formula. In our first example, we're going to use our new formula. We have the sum equals a sub 1 over 1 minus the common ratio. And we're going to plug in what we know. By looking at the formula that they give right here, we identify 4 as the a sub 1 and 0.6 as the common ratio. Now we plug that into the calculator. Okay, so the sum equals 10. Now remember from yesterday's lesson that an infinite geometric series converges to a number, right? Think back to yesterday's lesson where Jake was eating the pie, but he never actually ate the whole pie, right? Because even though his life went on forever, that infinite geometric series converged to one pie. Well, here, the sum of the terms of this geometric series converges to the number 10. So our second example, slightly different formula, but we know it's an infinite geometric series, so we're going to apply the same formula as before. So we have S equals a sub 1 over 1 minus r. Now we identify a sub 1 as 3. we identify R as 0.1 and plug that into the calculator. We get 3.3 repeating, which means this infinite geometric series converges to 3.3 repeating. So finite geometric series has a different formula, right? Obviously, finite means a specific number of terms. So we're not adding on forever. Notice this right here. It looks similar to the infinite geometric series, but it doesn't have the plus dot 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 on the end because it doesn't go on forever. We're going to stop adding terms at some point. And so that's how this is different. Now, when you use this formula, the common ratio cannot equal 1. So be aware of that. And we have the new formula, S equals A sub 1 times 1 minus R to the n over 1 minus R. So when given a problem, we identify it as a finite geometric series, and we know to apply this formula. All right, so here's our example. Find S sub 10 for the series 16 plus 24 plus 36 plus dot dot dot. Okay? Now, S sub 10, we know from our study of arithmetic series that S sub 10 means add up the first 10 terms of the series. This is what tells us that this is a finite geometric series because it's telling you straight out, hey, only add the first 10 terms. Not all infinity terms, right? Just the first 10. So we know it's a finite geometric series. We can see that A sub 1 is 16, and we have to calculate the common ratio. Think back to when we learned about geometric sequences. We calculate the common ratio by taking a term and dividing it by the term before it. So for example, I could take 24 and divide it by 16. We get 1.5. But I can't just do 1. I have to confirm that this common ratio exists over and over again. So now let's do 36 divided by 24, and we also get 1.5. So I'm identifying the common ratio as 1.5. So we know A sub 1, we know R. We can now plug into our new formula for finite geometric series. So here we go. S equals A sub 1 times 1 minus R to the n over 1 minus R. We just said that we're being asked to find S sub 10, so that's S sub 10. A sub 1 is 16. 1 minus 1.5 for R raised to the n power. Well, 10 is n, yep. Divided by 1 minus 1.5. So we plug this into the calculator, and we get 1,813.28. So the sum of the first 10 terms of this series, or the partial sum, we could call it, or the finite series, all of those things mean the same thing, is 1,813.28.